You're welcome to AFD'S Academy. I'm Arthur Francis Devan. In our previous video, we discussed about preparation of reagents, and in the preparation of reagent, we were able to know how to calculate various concentrations of acid or bases that may be required in terms of the given calculations that will be required, like I said. So, if, for example, we are asked to prepare 0.1 mole per dn cube of sodium hydroxide or H2SO4, we now know how to prepare that. And after which, we may likely use them for titration purposes and various other things, experiment which may be required. But for the sake of titration, there are other formulas which we will be needing. After preparing the reagent, we carry out the titrations and we get our endpoint. And having gotten the endpoint, we'll be able to use the endpoint to calculate certain other things like the molar concentration or the mass concentration, the relative molecular mass or the amount, and so on and so forth, percentage purity, what of crystallization, and all that. So in order for us to be in unison with this reality, today I will be bringing to us the various formulas which we may likely use if we want to deal with titration. So I'm going to give us all the formulas, the essential formulas which are required in terms of our titrational purposes. So let's start with concentration, molar concentration. In terms of concentration, we have the molar concentrations, we have the mass concentration. When we talk of molar concentration, just the difference is the unit. So, but it is important that when you see, for example, calculate the concentration of the acid in mole per dn cube, they are asking you to calculate the molar concentrations. If they say in GDM cube, they are asking you to calculate the mass concentration. So, but I'm going to differentiate them by saying molar concentration, the various formulas which you can use to get them. Mass concentration, the various formula which we're going to use to get them, and so on and so forth. So let's start with the molar concentration. So these are volumetric analysis formula. So let's take our number one, which is molar concentration. The unit is in mole per dn cube. So for us to do this, there are various other formulas. Let's take the first one, A, which is our CAVA over CB, VB is equals to NA over NB. Now, this, the CA means concentration, see, I write it in short, concentration of acid in mole per dn cube. CB means concentration of base in mole per dn cube. VA means volume of acid in cm cube or dm cube. VB means volume of base in cm cube or dm cube. Na means number of moles of acid, has no unit. Nb means number of moles of base. So, this is the first formula for molar concentration. We use this, the concentration of the acid or the concentration of the base. We use this formula to get that. So This CAVA in normal, how do you call it, acid base and salt reactions, which is neutralization reaction, this is what we use. But when we're dealing with redox titration, we have a different formula, a little different from this. Let me write it here. The C subscript OA means concentration of oxidizing agent times volume of oxidizing agent. Here is concentration of reducing agent times volume of reducing equals to number of moles of oxidizing agent over number of moles of reducing agent. The same unit. The concentration is in mole per dm cube, the same. Alright? So that's just the difference. When we are dealing with redox titration, that's what we use. We're dealing with acid-base titration. This is what we use. You must know the difference and when to use them. If you are dealing with redox and you use these, you're going to lose some marks for using the wrong formula. When you're dealing with these and you use these, the same thing applies. Okay? You're going to lose some marks in the process. So our first A, which is the concentration, molar concentration, I have to get the formulas for molar concentration. So this is the first, which is the A. Let's look at the B. B, molar con in mole per dm cube is equals to mass con GDM cube over relative molecular mass in G mole. Okay, this is our second formula for molar concentration. Molar concentration, we have to know what the mass concentration is. Sometimes it may not be given, so you're going to find it before you can substitute it into the formula. And the relative molecular mass of the compound, which if you're dealing with sodium hydroxide, which is sodium is 23, oxygen is 16, and hydrogen is 1. You add them together, you get what you want. Alright? Every compound we can determine the relative molecular mass of almost every compound, which probably maybe I'll make a video on how to do that. But by now, I think we should know that. Even if we don't, I will give us something so that we'll be able to make up for our lapses if we don't. So, C, we have another one which it says, so molar con in mole per dm cube is equals to amount in mole over volume in dm cube. So the unit for molar con is mole per dm cube. So you see that right here. So this is it. If this is true, it means that the volume that will be given in the equation thereabout must be in dm cube, which means if it is given to you in cm cube, you convert it to what? dm cube. That is important. You should know that. So these are the three formulas when we're dealing with molar concentration of substances. We use these three formulas to get that. So let us try mass concentration. This is okay. For mass concentration, we have A. So a mass con in GDM cube is equals to molar con in mole per dm cube times relative molecular mass in G mole. For you to know whether you're right from the units, this is mole. We strike out this mole. Indices says that in the laws of indices, when number with equal bases are multiplied, their powers are added. This is mol raised to power 1. This is mol raised to power minus 1. 1 plus minus 1 is 0. And we're left with g dn cubed, which is here g dn cubed for the unit of mass concentration. It is important, we know that. Let's take our B. We have mass com in GDN cube to be mass in gram over volume in dn cube. So this also is mass per dn cube for mass concentration. So with these two formulas we can get a mass concentration and we move on. So this is it. Let's see. I think this is 3 for amount in mole. A, amount in mole is mass in gram over relative molecular mass in G mole. So this will cancel this. The inverse of minus 1 is plus, which is 6. So this is the first formula for amount. You can use this formula to get anything you're dealing with in amount. Alright? So let's take another one on amount. B, amount in mole is equals to molar com in mole per dm cube times volume in dn cube. So dn cube will strike out this dn cube and we'll be left with mole, which is a unit for amount. Remember, like I said earlier on, indices says that when number with equal bases are multiplied, their powers are added. If I bring out this, I say dn raised to power minus 3 times dn raised to power 3. They have the same basis. This is dn raised to power minus 3 plus 3. And this is dn raised to power 0. Anything raised to power 0 is 1. So that 1 times mole is mole. So this is it. So this is amount. Let us look at mass in gram. Okay, that's 3. Let's take the first one. Mass in gram. This is amount is equals to amount in mole times relative molecular mass in G mole. Mole will strike out mole. I'll be left with gram for this. This is A. Let's take B. Mass in gram, which is mass concentration. Mass com in GDN cube times volume in dn cube. So this will strike out this. I'll be left with this for my mass. So all these I'm giving to us are the various formulas which we can use when we're dealing with volumetric analysis calculations. There are a whole lot of stuff, questions that we can be confronted with. So if we have a vast knowledge on how to get these formulas, then it becomes easier for us to move through, okay, without having much challenges. So let's take a look little more to complement what is left. All right, this is for mass. Let's take percentage of water of crystallization. For percentage of water of crystallization, A. In A, we have relative molecular mass of hydrated substance over the mass comm of hydrated is equals to relative molecular mass of anhydrous over the mass comm of anhydrous. Now, this is it. From here, we'll be able to get what we need. Let's have something like a practical explanation of this to see. Relative molecular mass of hydrated. Let's say the salt is calcium triiosocarbonate 4. It doesn't have .xH2O. This is a hydrated salt. If I calculate the relative molecular mass, this is 100 plus X18. Alright? Over the mass concentration, which I don't know, let's call that 3 GDM cube. For example, is equals to that of anhydrous become calcium triiosocarbonate 4. There is no water in it, this anhydrous. So this become 100, for example, this become 100 over the mass call, let's call it 20 GDM cube. So here, remember I said this is 100 plus X18, the relative molecular mass. So first, for you to have this formula means we want to know what the value of X is, which is the unknown, the number of moles of water of crystallization present in here. So we have to make 100 plus X18 over 3 GDM cube is equal to 100 G mole over 20 GDM cube. We make X a subject of formula to know the number of moles of water of crystallization as to know whether it is dihydrate, trihydrate, pentahydrate, hexahydrate, decahydrate, whatever it is. So when you get that, before you can proceed further to do any other calculation which is required. Okay, to check the percentage of water of crystallization. So this is A. If this were to be A and my B is to get the percentage of water of crystallization. So it becomes, the B will become the value of water, which is X18, over the total compound, which is 100 plus X18 times 100. This becomes a percentage of water of crystallization. Okay. For percentage purity, we have stuff like, okay, 1A, percentage purity is equals to the mass comm of the pure sample over the mass comm of impure sample times 100. This is for percentage purity. Let's call it D. For percentage impurity, we say, okay, for us to, let's take D to be another one. Percentage purity plus percentage impurity Then C, if I from here, if I want to get my percentage impurity, become percentage impurity is equals to 100 minus, percentage impurity, that's wrong, percentage impurity plus percentage purity is equals to 100. So for me to get my percentage impurity becomes 100 minus percentage purity. Yeah, percentage purity. Okay, this about that. Remember, for you to be able to apply this, you must be able to calculate the mass concentration of the pure. It will be given to you that the mass concentration of the pure sample is this, or impure sample is this. As the case may be, one must be given, you get the other one. So these are the required formulas which we need in order to move easily or survive easily when it comes to the volumetric analysis calculations. And our ability to put them in our head, it's very important because it will be able to enable us to help us, assist us to achieve those basic goals which we need. We move swiftly in terms of our operation when it comes to our calculations generally. And also, like I said, you cannot be a good chemist if you do not have a formal knowledge of mathematics, because all of these which I've given to you right now has to do with calculations and the applications of certain other mathematical topics like change of subject of formula, which is very pivotal in this whole arrangement. So it is imperative and important that we should know how to run through this whole thing and get ourselves acquainted to them. So do not forget to subscribe and press the like button, and also the notification bell, have it on so that whenever I have a video uploaded, you'll be able to get that. Thank you so much and have a wonderful time.